We are creatures born to gravity. From the moment we draw our first breath, we live in its quiet embrace. It shapes the fall of rain, the rise of oceans, the beating of our hearts. It tethers the moon to our skies, our feet to the soil, our sense of up and down. But the moment we leave Earth, we step into a void where gravity vanishes. And with it, the rules change. Muscles forget how to pull. Bones forget how to carry. The heart forgets how to push blood upward. And slowly, silently, the body begins to drift, not just in space, but in memory. We have learned to endure microgravity, to adapt for days, for weeks, for months. But now, as humanity prepares to leave Earth for longer than ever before, to build outposts on the moon, to travel to Mars, to cross the vast distances between worlds, we must answer a pressing question. Can we bring gravity with us? Artificial gravity, a science fiction dream that is rapidly becoming a scientific necessity, a technological bridge between what we know and where we are going. Gravity is the quiet architect of life. It is not just a force that pulls. It is a scaffold upon which biology has been built for billions of years. On Earth, gravity has shaped the way blood flows through arteries, how bones grow dense, how muscles flex with each movement. Even the vestibular system in our inner ears depends on gravity to sense motion and maintain balance. In space, this architecture begins to unravel. Within days of microgravity exposure, fluid shifts toward the head, swelling the face, compressing the eyes. Vision can blur. Pressure inside the skull increases. Within weeks, the body begins to unbuild itself. Bones begin to decalcify. Muscles shrink. The spine elongates unnaturally. Even sleep patterns and circadian rhythms begin to falter, no longer guided by the sun's predictable arc or gravity's downward pull. And beyond the body, gravity influences our mental map of reality. It helps us know where we are. When it disappears, so can our sense of direction, even our sense of self. Without gravity, we become aliens to our own physiology. And no amount of exercise or pharmaceuticals can fully substitute for the constant, gentle tug that Earth has always provided. If we cannot take gravity with us, perhaps we can simulate it. Artificial gravity, as a concept, does not attempt to duplicate the mass of a planet. Instead, it uses motion to mimic gravity's effects. The key lies in acceleration, specifically centrifugal force. Spin a bucket of water and it clings to the sides. Not because gravity has changed, but because motion creates a new reference frame. Inside that spinning frame, outward pressure feels like gravity. This principle, tested on carousels and centrifuges, is at the heart of artificial gravity design. In space, a rotating structure can replicate this effect. The outer walls of a spinning habitat become the floor. The faster the spin, or the larger the radius, the more Earth-like the sensation. But achieving balance is everything. Too small a radius, and the spin must be too fast, causing dizziness, disorientation, and nausea. Too large, and the engineering becomes complex, massive, and expensive. Between these extremes lies a narrow band of possibility, where physics meets feasibility. Building a spinning spacecraft is not like building a wheel. In space, nothing is simple. Rotation introduces a host of challenges, from navigation to structure to safety. Imagine a spacecraft spinning like a bicycle wheel. Now imagine docking another vehicle to its hub. The rotation must stop or be matched exactly. Inside the spinning section, plumbing systems must function under constant outward force. Every bolt, pipe, and wire must withstand continuous stress. Coriolis forces, experienced when a person moves radially inside a spinning environment, can cause confusion and motion sickness. A simple turn of the head can cause a swirl of dizziness. A cup of water poured out won't fall, it'll slide sideways, following the curve of the station. To make artificial gravity usable, engineers must balance all of these variables: spin rate, structure, transitions, energy efficiency, and human comfort. NASA, ESA, and private companies like SpaceX and Blue Origin are studying multiple models: modular habitats with rotating arms, tethered systems where two masses spin around a common center, even ring-shaped space stations reminiscent of science fiction dreams. The idea of artificial gravity is not new. As early as the 1900s, visionaries like Konstantin Tsiolkovsky imagined spinning habitats in space. Later, scientists like Wernher von Braun popularized the rotating wheel station, an idea immortalized in cinema with films like 2001: A Space Odyssey. But we have yet to build one. Why? Because we've lacked the urgency and the funding to justify it. Short-term missions to low Earth orbit or brief lunar visits could function without gravity. Exercise and medication could patch the gaps. But Mars changes everything. A round-trip mission could take 2 to 3 years. Extended stays on the Moon may last months. The longer the duration, the more dangerous the absence of gravity becomes. Experiments on Earth and in orbit, using short-arm centrifuges and rotating test beds, are beginning to provide data. They're exploring what minimum level of gravity is required to maintain human health. Do we need 1 g? Or would 0.3 g, like on Mars, be enough? Could we dose gravity intermittently, like medicine? These questions are now more than theoretical. They are mission critical. Imagine waking up in a space station where gravity feels real. Your feet press against the floor. A cup of tea stays in the mug. You walk, not float. The shower has water pressure. The toilet flushes. Your bones and muscles engage like they do on Earth. In a rotating habitat, life could feel strangely familiar, yet subtly different. Down is not toward a planet, but outward, toward the hull. A dropped object falls not straight, but slightly curved. Standing still may feel normal, but walking radially or tangentially may require adjustment. Artificial gravity doesn't eliminate the need for adaptation, but it restores a crucial rhythm to life. It allows routines, tasks, and health to unfold more naturally. And perhaps most importantly, it preserves the psychological comfort of physical normalcy. For astronauts facing months of isolation, a dose of normalcy may be just as vital as air, water, and food. Our next steps in space will not be flags and footprints. They will be homes, habitats that must support human life for months or years. And gravity, artificial or otherwise, will be central to their design. On the Moon, 1/6 gravity may preserve some function, but for long-term lunar bases, artificial gravity pods may still be needed to restore health between EVAs. On Mars, the situation is different. The red planet has 38% of Earth's gravity, perhaps enough to maintain bone and muscle, but perhaps not. Only time will tell. Artificial gravity habitats, on the surface or in orbit, could provide insurance. And for the voyages in between, the months-long transits to Mars, or deep space missions to asteroids, or even Jupiter's moons, artificial gravity may become the most important life support system of all. The story of artificial gravity is not just about space. It is about us, about the limits of the human body, the elasticity of biology, the creativity of engineering. In seeking to recreate gravity, we are not defying nature. We are honoring it by recognizing what gravity has given us and what we must preserve in its absence. To build artificial gravity is to build a bridge between Earth and the stars, a promise that wherever we go, we will carry the conditions for life with us, not just food or air or water, but the unseen, unfelt force that holds it all together.